All right, so we're going to talk about fluid and electrolyte balance. All right, first, let's talk about fluid compartment. We have lots of fluid in the body. There's fluid in the cells. That's intracellular. We have fluid outside the cells, extracellular. This would include um, interstitial fluid, and other extracellular fluid, things like plasma, spinal fluid, and that. Right, so inside the cells, outside the cells. There's a lot of stuff floating around in this fluid. It's mostly water, solutes dissolved in the water. We're going to focus on that idea, the movement of water between fluid compartments. It's not ideal that we have that. Mostly what we get is two-way flow, meaning that water's going in the cells, it's going out of the cells, but it's going in and out of the cells at an equivalent rate. The issues that occur here is when we have water either going into the cells or water coming out of the cells. And that's accomplished with osmosis. And osmosis is, of course, that diffusion of water. Water follows around those dissolved particles. We're not actually moving water. Water's just following around solutes. Let's take a look at that idea. So here I have the outside world. Here we have our extracellular fluid. And here we have our intracellular fluid. Now, if water that is here goes there, well, extracellular fluid, there's water, there's lots of dissolved particles in the water. So what you're left with if you lose the water is the dissolved particles. Now, the concentration of stuff over here is increasing because you're losing the water. Think about boiling tap water. You're left with like this white film at the bottom or chunks of white stuff because they're precipitating, they're becoming more concentrated as the water evaporates. So here, as water leaves the extracellular fluid compartment and leaves the body, you're left with more concentrated there. So what's going to happen? Water follows osmosis, the dissolved particles. Water moves to the area of higher concentration. So to balance it out, water that is here is going to go there. Molecules spread out further, but we've lost water from that intracellular fluid compartment. This would be your mechanism of dehydration. So now water has left these cells and has moved out to the extracellular fluid. Because the tonicity here has gone up, this is now hypertonic to the cells. Now, what if we run this the opposite direction? All right, so now what if water from the outside is going to come in? Well, now we've diluted the extracellular fluid. We've added that water to this extracellular fluid compartment so the particles are spread out further. Water goes to the area of higher concentration, so that water is now going to go into the cells. And the cells are going to swell up. This is what we will call hypotonic hydration. Now, both dehydration and hypotonic hydration are issues. Our ion that we're concerned with here will be more likely not sodium. In essence, dehydration is basically what we would call hypernatremia. That's too much sodium in plasma. So now, again, the plasma is an extracellular fluid, so water is going to leave the cells and go out to where that higher concentration is. Dehydration is your major cause of hypernatremia. It's rare that you see hypernatremia outside of dehydration. It's not impossible. And it does happen outside the realm of dehydration when you've ingested so much sodium that we get hypernatremia. It's often life-threatening. This is going to sound weird, but it will kill you ingesting that much sodium. It's not easy to do. We're talking about death by drinking soy sauce. More on that later. I'll post a link to an article on soy sauce related deaths. I'm not even kidding. And the statistics of people who die from ingesting excess amounts of soy sauce. On the opposite end of that hypotonic hydration. Hypotonic hydration essence of hyponatremia. It's not that you don't have enough sodium, it's that we've diluted the plasma by putting so much water in it that it's the same principle. It's like we dilute. Now, hypotonic hydration is often referred to as water poisoning. And it can also be fatal. Because what's going to happen is we bring in this water into the blood. That same water is going to go into the cells, which are going to swell up, and into other fluid compartments, the interstitial fluid. And so then we get the accumulation of water in the interstitial space. This would be edema. The accumulation of fluid in the interstitial space. Hypotonic hydration is going to be highly associated with either pulmonary edema or cerebral edema, both of which will be life-threatening issues. As fluid builds up in that cerebral spinal fluid and fluids moving in, pressure builds up in the skull and will damage the brain. Or you get pulmonary edema and we fluid in that interstitial space and we can't get oxygen and carbon dioxide to move through those fluid barriers. We see cases of this more often than you would expect. Possibly the most well-publicized case of hypotonic hydration happened several years ago when the Nintendo Wii was a thing. A radio station held a contest. It's called Hold Your Wii for a Wii. And the gist of the contest was they had these contestants, and they had to drink as much water as they possibly could in a period of time without either vomiting or peeing. Medical professionals called in and said, "You're going to kill somebody. Such a thing as water poisoning. They're going to die." They didn't believe them. And so they had this contest, and one of the contestants went home and died of cerebral edema. She didn't even win the Wii. So kick them when they're down. Other cases that you see aren't as well publicized, but often happen in infants. Infants and the elderly are most susceptible to fluid imbalances because their state of hydration is a bit more precarious. Infants have a lot more body water content than normal adults, and older people have a lot less water content than your average. In an infant, we'll see cases of hypotonic hydration because parents are diluting formula. There's a ratio of water to formula on the back of the can that you're supposed to mix. And if you dilute that, then you're giving the baby more water than it should have. And you're creating a hypotonic hydration. And every once in a while, you'll have a couple that's charged with either neglect or manslaughter for accidentally killing their kid by diluting that formula instead of mixing it as intended. So this is mostly what we're concerned with fluid balances. Electrolyte balances, we're not concerned with all of the electrolytes, really. Sodium is the major cation of the extracellular fluid. You need to know that. You need to know that sodium isn't outside the cell, extracellular. Inside the cell, potassium. Sodium outside, potassium inside. This is because of that sodium-potassium pump we're pumping. 3 sodium out, 2 potassium back in. Yes, that potassium leaks right back out, but thanks to the kidneys, that potassium will be lost to the urine. Sodium imbalances are typically water imbalances. It's rare that you would have someone who doesn't have enough sodium in their diet, especially in the United States. It's too much sodium in the diet is again more of an issue for people with hypertension or especially the elderly and elderly people who are prone to swelling of the extremities, edema of the extremities, will be told to go on a reduced sodium diet to stop that fluid retention because water follows sodium around. The more sodium you're bringing in, more water you're going to retain. Potassium imbalances are different because potassium imbalances are always a medical emergency. They are life-threatening very quickly. Potassium is involved in setting resting membrane potential of the cells. Too much potassium in the blood is hyperkalemia. Too little potassium in the blood, hypokalemia. Either one of these will be life-threatening in a hurry because it disturbs the resting membrane potential of the cell. And this is particularly going to affect the nervous system and the cardiovascular system. So let's think about this idea. Remember, you've got resting membrane potential that's really set up by that sodium-potassium pump. Now, we're pumping sodium out to potassium back in, and we set an electrochemical gradient here. Some of that potassium leaks out until we reach sort of an equilibrium thing, and we've got that voltage. Now, we're pumping potassium back in against its gradient. If I add a ton of potassium out here, well, now the potassium that's here doesn't need to leak out anymore. It won't leak out. It stays there. And so now the inside of the cell is not as negative as it was. It's getting closer to that resting membrane potential. And you'll depolarize the cell. When we're talking about this at the heart, it's going to stop the heart. This is a potent way to do it in open heart surgery. For instance, we talked about Bennett. When Bennett had his open heart surgery and they stopped his heart, they did that with potassium. And for a little while, his heart stopped beating. If the state of Texas determines that you need to die for your crimes, they're going to inject you with potassium chloride, and it's going to stop your heart. Now, hypokalemia is not enough potassium, and this is just as big an issue because now you're going to get more potassium coming out of the cell than you should, and the cell membrane will hyperpolarize. So now it can't fire an action potential, and again, your heart's going to stop. So too much, too little potassium, either way, your heart will stop. Luckily, you have kidneys, and the kidneys are managing this potassium level of the blood. Potassium levels are maintained by aldosterone. Aldosterone causes sodium retention, potassium excretion by the kidney. It's going to act at that distal convoluted tubule of the nephron, the very last part of that, where we're fine-tuning the concentration of urine. So that's aldosterone. Triggers for aldosterone release include angiotensin 2 and hyperkalemia. If the potassium levels of your blood go up, your adrenal gland's going to release aldosterone, and the aldosterone is going to cause you to get rid of that potassium. Patients that are suffering from long-term kidney failure are going to be told to avoid salt substitutes because often they're potassium chloride. Kidneys suck. They're not going to be eliminating as much potassium as they should be, and so you're at a higher risk of anemia. There are other electrolytes that we care about. Calcium, levels of calcium are, of course, hormonally controlled. We've talked about parathyroid hormone in depth. We have anions like chloride. Chloride homeostasis is basically sodium homeostasis. They go together. All right, so there's a little bit more detail here in your blackboard. What I'm trying to do at the moment is sort of hit the big picture points of this, what we're really concerned with in terms of both fluid and electrolyte balance, and take a look at where this is going to be more clinically relevant. All right. My next post here will be a bit more in depth, and we're going to go back and review and probably introduce some new stuff because I know there's stuff that we've skipped over, and I realize that we're behind here. We're all trying to play catch up. But my next post will be a review of everything, and we're going to get ready for the exam. So I suppose important announcement. So exam stuff. So the question that I've gotten is, when is the exam going to be? My answer for you there is, it doesn't really freaking matter because I'm going to post it on Blackboard, and I'm not going to limit the time. That sounds stupid because I'm just going to leave it open. You only get one shot at it. You're not going to be able to go back and correct it. But I'm going to leave it open for at least a long period of time. It's probably not going to be indefinite. But there's going to be a large window here. The reason for that is at least 2 of your classmates have tested positive for our current pandemic. And because of that, I don't want to constrain this too much. I don't know what's going on with them. They may have health issues. Well, they obviously have health issues they're worried about. They may have family members with similar problems. I don't want to do that. I don't want to put pressure on you guys. I know what it's like. Believe me, I know what it's like. There are 6 kids running around this house. The reason I keep posting these in the middle of the night, that's when they're asleep. So yeah, I love these notes from the school. Homeschool your kids now. Like, great, thanks. I'll homeschool my kids while I'm teaching 100 other people on the air. So between meals and 75 snacks a day, and whatever, we'll get this. But by no means am I going to tell you like your exam is Thursday between 2 and 4. That's just ridiculous. So after we do the review, um, I'll work out the exam. I'll get it posted. We'll be there. All right. So for the lab part, there will be some diagrams. Um, Look at the video that I've got of the respiratory anatomy. I'll find something for renal anatomy. I did not get a chance to video the model with that, and I just ran out of time. In sneak back on campus, I'll snag some of those models that needs to be seen. But the lab part will be both respiratory and renal anatomy. It will be on diagrams, and I'll get that set up on Blackboard as well. With that, I'll have grades posted soon. Sorry, I'm running so far behind on that. It's been a month. So I hope you guys are taking care of yourselves, following all the guidelines. Here, as we do this, um, just sort of as a preview, and as you go back and you look at your notes and you study stuff, make sure that you keep your eye on big picture ideas. I haven't had the time to go into the minutia that I normally would. We haven't talked about some of the mechanisms of the kidney maintain the glomerular filtration rate and this sort of thing. We'll touch on that in the review, but again, for this part especially, we're big picture ideas. Now, after this, after we just sort of push through this renal respiratory thing, we're going to come back with digestive metabolism and reproduction. And that will wrap up the rest of this. At this point, your standard notes on Blackboard are ancillary to what we're going to be focused on here. I'll tie back into them as necessary, but make sure that you pay attention to what we review here. And we'll go over some other things. As you can tell, I'm getting better at this whiteboard thing. My handwriting's a little more legible, and that whiteboard ink is epic. Like, I wish I had that marker to write with on the board in class. Is that like stars? What? That'd be awesome. All right, so we're gonna end there. Check out the other videos. Make sure that you watch the lab thing and acid-base stuff. Office hours. That's right, office hours. So I'm gonna try to do this over the weekend, and I'll announce it at some point, what time and whatever. But I'll send you a link in your email to a Zoom meeting. and I'll set up my camera stuff here, and we'll do that. You can ask questions, and we'll review, and it's going to be great. Everything's going to be fine. So if you have any questions right now, feel free to give me an email. Friend me on Facebook, whatever you have to do. And we'll get this worked. As soon as we push through this, things will smooth out as we get the digestive and metabolic and we wrap up the rest of this. The lab for that is ridiculously easy. And a lot of the physiology you will already be familiar with. So that's it for now. If you're commenting to tell me that you're watching this, make sure that if your screen name is not your name, that you tell me who you are. I'm looking at you, you're King54. No idea who you are. So if you're in my class, make sure that you tell me. Like things, it makes me look cool. And if you're bored, look at some of my AMP1 videos where I electrocute myself with a TENS unit to demonstrate muscle contraction.